Yeah, so this isn't going to be exactly a continuation of yesterday's talk. I'm going to just go over the parts of yesterday's talk that you may have seen really fast, and then hopefully move on. All right. Okay, so the title of the talk is Collaborative Filtering with Low Regret. We want to give recommendations, say, imagine Amazon or something. So the setup is pretty simple. There's a bunch of users, a bunch of items. You can think of them as arranged in a matrix. All right, and there's some true value. Let's think binary, so +1, -1. You like or dislike an item for each user and each item. But obviously you don't see this. And what you would like is to, like one by one, give the users items that they like, right? But the point, the reason why this is not obvious is because you don't actually see this. So just a bit of notation. There's L, U, I is the entry of this matrix. Okay, so once we have this notation LUI, we're going to think of a user actually as sort of equivalent to the row vector of the items. So LU dot, it's a vector. We can also think of an item as corresponding to the column vector. So I might say something like items are similar to each other. All that means is if you look at the columns are similar, and similar, say, according to some cosine distance, or their inner product is relatively big. Okay, so now the way this works is kind of work sequentially, one by one. So at time 1, 2, so on, you recommend a new item to a user, and they give you feedback. They either like it or dislike it, and then you continue. Okay, so this is just sequential, one by one, filling in entries of this matrix. So let's write it. I'm going to emphasize this new. Deborah emphasized it yesterday. And it's important for various reasons, and we'll go a little bit into that in a moment. Okay, so we're going to recommend item I sub t to user u sub t. User u sub t is going to be uniformly at random selected from the whole pool of users, which there's n. So I'm going to add an n here. N is important. Don't forget what n is. It's the number of users in the system. Okay, so you recommend an item to a user. It's a new item. So you don't recommend the same movie over and over again. Then you get feedback. Think of this as bandit feedback, right? So you just get feedback on the thing that you chose. Okay, great. So this is the setup. How do we measure our performance? So expected regret is what we're going to use. At some arbitrary finite time t, the expected regret is normalizing by number of users, expected value of sum over all the times, 1 minus this L of u t I t. All right, so we're comparing ourselves to what you would do if you just gave a good recommendation. That'd be +1. And so this regret is 2 if you gave a bad recommendation, and 0 if you gave a good one. So obviously you want a low regret. That's good performance.
Normalize with n and not with t?
That's a good question. It's sort of arbitrary how you normalize it. But yeah. Oh, sorry. Maybe that's.
Oh,
okay. So each. Yeah, good. Now it's better, right? Okay, so good point. Okay, good. So yeah, at each time you recommend a new item, and so yeah, okay, good. So 2 things to emphasize, and I won't go into details, is that this looks like a matrix completion problem. It sort of is, but it's different than the standard formulation where you observe an entry, or some random subset of entries, and just want to complete the whole matrix. It's online. In theory, you can adapt to what you've recommended so far, and so on. So it's a different setting. Also, this regret is different than the standard performance metric for matrix completion. Okay, and then one other point is that, so this looks like a multi-arm bandit problem in some ways. It's actually different. And one of the key differences is that you recommend a new item, and that contrasts strongly with the multi-arm bandit notion of optimality, which is basically to recommend the best item over and over and over again. So that's not so good if we're doing recommendations. So okay.
Column or new entry?
New entry. Yeah. Okay. So, okay, final bit of notation. So probability that a random user, I'll use better handwriting, likes random item. So I'm predefined as new. And this is some constant. You can think of it as like a third or something. Okay, so theorem.
Sorry, guys.
Yeah.
So the setup is like the world randomly picks a user.
Or you can think of the user randomly decides to log on to Amazon and wants a recommendation.
Okay.
Yeah.
And then you're tasked with picking an item that they haven't been shown before.
Yeah. So okay, good. So this is a sort of extreme situation where whatever you recommend to them, they consume it, and then after they've consumed it, they don't want the same item again. Yeah. Okay. So the theorem is this plot, and Devrut sort of showed it. I'll just go over it very quickly. Okay, so we're going to plot the regret at time t as a function of time. So initially, if your recommendations are useless, they're completely at random, then the slope here is going to be 2 minus 2 nu. Okay, and this is just random guessing, and this happens until some time that we call t cold start. After this time, things get better. One gets a sort of concave down looking thing. And it's linear. And the regret scales like big O of t to the d plus 1 over d plus 2. Okay, and then finally there's this t max, at which point the slope doesn't decrease and there's some fixed slope, which is a function of the number of users and gets smaller as the number of users increases. Okay, so t cold start is a constant. So 2 over nu to the power roughly some constant times d, and I'm not actually going to say what d is. I'll just say roughly what it is. And then t max is equal to some constant times number of users, d plus 1 over 4d plus 2. Okay. Okay, so d. And Devrut spent a little while kind of discussing this, and I'm not going to discuss it at all, but it's the measure, it's a certain measure, I'll say a measure of complexity of item space. Okay. Good, so what are the goals? So in the remaining...
What's the distribution that you're drawing the users or items from?
Good, so at the moment there is no distribution. You can just think of, there is some matrix.
Otherwise you run into
P random user likes random item.
Be able to say to them.
Oh, this is new. If you were to select the random entry of this matrix, it's essentially the density of plus ones. So.
It's like you're given a matrix.
I mean, you aren't given it, but it exists. There's some, the assumption is that there's some true preferences of people. You don't know what it is, and then you go one by one, okay? All right, so what are the goals? I guess I have roughly 9 to 10 minutes. So there's 2 goals. We want to understand very briefly, Devrut mentioned item-item collaborative filtering as compared to user-user. And we'll get some intuition, these 2 really quick. And then why can we hope for sublinear regret, and what does that mean, and why is that good? Good. Why sublinear regret, and how do we achieve it? We'll see. Maybe only get into the first one, but hopefully the second one. So, okay. So we're going to start with an example. Right. So obviously the high-level goal is to get the best possible regret. So if I were to get a regret that looks like this, then that's better, right? It's lower. Yeah.
Sorry, if instead of this setting, you're just in a setting where you're allowed to pick any user item pair that's not yet been queried?
So meaning you can choose which user you're giving a recommendation to.
Is it actually strictly better, or?
That's a good question. I'm not totally sure.
Okay. I mean, there's a lot of settings where that's actually the setting you're in.
It's debatable, yeah, but yeah, we can talk about it. It's good. Okay. All right. So there's an example. We're just going to look at an example matrix and see what we can do. So this example matrix is going to have a block form. I'm going to shade in if the whole block is +1. And otherwise, it's all -1. Okay. Good. So let's just really briefly see what does user-user collaborative filtering do. And Deborah mentioned this. Well, you find a user that's similar to you. So by the way, I'll just emphasize there's n users here, but there's only 4 sort of types of users.
If n is 1, then things break.
If n is 1, then it's not so good.
But where does that show up in the theorem? Yeah, that's what I don't understand.
N1 should be impossible to do.
Yeah. Because you have an infinite number of items, right?
Well, so epsilon n is going to be effectively this, if n is 1. Right? So you could have just 1
So
here.
this is with hidden in the constant C.
Absolutely.
So n has to be just larger than some fixed constant, 50?
I mean, the performance gets better and better as n gets bigger. Doesn't have, I mean, n could be 1. And that's,
Then where does this break if n is 1? Or why don't you?
I don't think it breaks, but I think the slope here is just the same. So, and sort of T max ends up being,
There's no sublinear portion.
there's no sublinear
So
portion.
if you have an IID matrix, again, there's no sublinear portion, right? It's just a 1.
Oh.
Yeah. Okay, so user-user collaborative filtering. Step 1 is find a user similar to you. What that means is if you're a particular user here, so this is maybe I, user will be user U, and this is some other user W, then these two users have identical preferences, right? The rows are the same, so we say these are similar, and maybe some other users are different. So you find a user that's similar, and then you recommend an item that they like. So, okay, so user U, user W has liked this item. You can recommend that to user U. Okay, and the basic idea behind finding a user that's similar is you're comparing these two rows. Okay, so you're going to you reveal some of the entries in the two rows, and you decide they're similar if most of the revealed entries are in agreement. And you can convince yourself that under most situations it takes log k entries revealed, where entries where k is the number of blocks. So k types, there's going to be k blocks. Sorry, k groupings. Whatever. K types of users, so k groupings here. There's going to be also k types of items, and just an example. So here it's 4. All right, so this is just the first thing is I want to compare two users. Are they similar? I need a bunch of items to measure if they're the same. Right? This is sort of an exercise you can check. Okay, good. So I'll have enough time at least to compare user, and item. Okay, so item, collaborative filtering. Find item similar to item I like, and you recommend it. The basic thing that one does here is the similarity between items, and this is sort of the punchline of the whole thing, the whole paper and the whole result, is that it's actually pretty easy to compare two items. So this is item I, item J. Okay, and item I and J are similar if most users agree on them. Now you can ask yourself, how in the world am I going to figure out if two items are similar? I just can sample a bunch of different users, have them rate both items, and I can get an estimate of the inner product of these two columns. Right? So this seems sort of trivial. I'm comparing rows and I'm comparing columns, but there's actually something interesting going on, which is that the users can do this in parallel, right? You can have all the users, or a bunch of users, rate two items and get a really accurate measure of their similarity. If you want to check if two users are similar, then from the user's perspective, they have to rate a bunch of items. So it's costly and it's painful. Okay, so let's see. I guess I have 3 or 4 minutes. Because this is one insight, and this, without going into details, this shows that you can start giving good recommendations really fast. Okay, Deborah mentioned a little bit the cold start. The idea is you can just quickly tell which items are similar to the ones you've seen and give those. And so that gives rise to an algorithm which is based on a basic subroutine. The basic subroutine is check whether two items are similar. And you just query a bunch of users on both the items. You can check if they're similar. The algorithm that results from that, give a little bit of a picture. So you start by, so you can think of each item according to here as a n-dimensional +1 - 1 vector. So we have all the points here. Now by these queries, we can put an edge if two items are similar. So we can partition the space into items that are similar to one another and draw sort of a bubble here. Okay, so the algorithm has this sort of exploration phase where it determines subsets of items that are similar to one another. You could think of it as constructing an epsilon net. Okay? And then if you want to start giving recommendations, what users do is they check an item. So maybe a user rates this item, and if it likes this item, then probably the user will like all the rest of the items that are similar to that item. So then you can recommend all of those. Okay? And if a user doesn't like this item, then you can just toss out all of these. Okay, so there's sort of two phases. One, you use the parallelism to quickly determine which items are similar to which other ones. And then you can have individual users sort of find which groups they like. Okay, so going back to a regret picture, in order to get this initial sort of clustering of the items, the similarities, it takes some small amount of time that it's shared among all the users. And then things get better and better. And the reason why they get better is because you can refine the accuracy of your partition. Okay, so this similarity measure is going to get more and more refined, and you start getting better and better recommendations because these items are more similar. It's a high-level algorithm. I guess I'll stop there. Take any questions. Yeah.
So the question, I mean, what if there's two types of users that are very different?
Perfect. Yeah.
So how does this discover that? Right, one type of user has the exact opposite preference of the other type of user. And so you compare two items and you say, these items are similar, but half the users like it and half don't, right?
Okay, so this would be this kind of situation. There's user type 1, user type 2. If the two items are similar, then the user will agree on that item. So I can think of it from either perspective, but if I'm trying to recommend an item to this user, I can look at this column, I can find another item that's similar. It comes here, and the user will. So one way you can think of the items being similar as most users agreeing on that item.
I feel like you can probably build counterexamples as they get bigger, right? So in this case, right, if two items are similar, it's also that the groups are similar. So like the item is telling you the group as well, the user group.
So that's a general thing that's true, is if you specify the structure over the items, that determines the matrix, and that determines, therefore, the structure over the users.
So Glenn, I also have a question. So first of all, theorem is achievability and converse, right?
Good. So the converse is still in progress. It hasn't been finished yet, but there will be a converse soon. Yeah.
Another question. So it seems to me, I mean, for a fixed matrix, right? What can help you gain? I mean, the only side information you have is that new parameter. How about the following algorithm? So each time you have to recommend something, you just look through the columns and see which one has density of revealed entries, below new. So then, roughly you expect a good lots of +1s in that column. So then you kind of bias your recommendation towards that. Because
so there's something going on that I glossed over. That's aside from just how good the item is in general. There's something that allows you to find items that are similar to one another. And that's what allows you to give good recommendations. It's a certain structure in the space of items. And there's all this stuff with this dimensionality of the item space and things that I didn't go into. Right, but if I know that these items are actually identical, then I'm in good shape. Because once a user finds that they like one of them, they're for sure going to like the other items. Because all users agree on those items.
This is what D is.
D is somehow related to how hard it is to...
D is a parameter of a matrix.
D is a parameter of the matrix.
Ah, okay.
Sorry, yeah.
No, so new is not the only parameter.
D is a parameter of distribution, not of matrix.
So forget the distribution, yeah. So there's D, there's N.
There's no distribution?
Think of D as a parameter of the columns.
There was a distribution yesterday at the beginning.
Yeah. So I let go of the distribution for simplicity, but yeah.
Later, because we have one more talk this morning than we have had all the other mornings.